Hi, welcome to the second lesson in Introduction to Quantum Computing. In today's video, we will discuss the qubits. So let's start. Qubits, short for quantum bits, are the fundamental units of information in quantum computing. Unlike classical bits, which can represent either a 0 or a 1, qubits can exist in a superposition of both states simultaneously. This is due to a property of quantum mechanics called superposition. Qubits are the building blocks of quantum computing, where complex quantum algorithms can be implemented to solve certain problems more efficiently than classical computers. By utilizing superposition, entanglement, and quantum gates, qubits offer the potential for powerful computational capabilities and advancements in areas such as cryptography, optimization, and simulation. The characteristics of quantum bits can be described as superposition. Qubits can be in a superposition of states, meaning they can simultaneously represent both 0 and 1. This is different from classical bits, which can only be in one of the two states at a given time. Quantum states. A qubit state can be represented as a linear combination of the basis states, 0 and 1, often denoted as alpha 0 plus beta 1. Here, alpha and beta are complex numbers called probability amplitudes, which determine the probability of measuring the qubit in either state when observed. Measurement. When a qubit is measured, it collapses into one of the basis states with a probability determined by the squared magnitudes of the probability amplitudes. For example, if a qubit is in the state alpha 0 plus beta 1, measuring it will yield either 0 or 1 with probabilities alpha 2 and beta 2, respectively. Entanglement. Qubits can become entangled, meaning the state of one qubit becomes dependent on the state of another qubit, even if they are physically separated. Entanglement is a crucial property for quantum information processing and enables certain quantum algorithms to outperform classical ones. Quantum gates. Operations called quantum gates can be applied to qubits to manipulate their states. These gates are analogous to classical logic gates but operate on the quantum states of qubits, allowing for various computations and transformations. No cloning theorem. Unlike classical bits, it is impossible to make an exact copy of an unknown qubit due to the no cloning theorem in quantum mechanics. This property has implications for quantum information security, as it prevents unauthorized copying or eavesdropping on quantum information. In classical computers, information is represented as the binary digits 0 or 1. These are called bits. Quantum bits or qubits are similar to bits in that there are two measurable states called the 0 and 1 states. Now let's talk about mathematical representation of qubits. Dirac or bracket notation is commonly used in quantum mechanics and quantum computing. The state of a qubit is enclosed in the right half of an angled bracket, called the ket. So what is the relation between superposition and qubits? The superposition property of qubits allows quantum computers to perform certain calculations much faster than classical computers. It enables parallel processing, as a quantum computer can perform multiple calculations simultaneously by leveraging the different possible combinations of states that the qubits can be in. Amplitudes, on the other hand, are very important because they give us the probability of finding the particle in that specific state when performing a measurement. The probability of measuring the particle in state can be shown as this equation. In quantum computing, understanding matrix is also an important task. In matrix representation, a qubit is written as a two-dimensional vector where the amplitudes are the components of the vector. These are commonly known as rows and columns in the conventional matrix. Quantum states in quantum computing are often represented on a block. Spheres and operations in QC amounts to moving the state around the block sphere is a geometric representation of the quantum states of a two-level quantum system, such as a qubit. It provides a visual representation of the state space of a qubit and is named after the physicist Felix Bloch. The state of a qubit can be described by a vector on the surface of the Bloch sphere. This vector, often referred to as a Bloch vector, points to a specific location on the sphere corresponding to the quantum state of the qubit. The length of the vector represents the magnitude of the superposition, and the direction of the vector determines the phase relationship between the basis states. As quantum computers are based on fundamentally different concepts than classical computers, they must be built from completely different technology, i.e., it is not possible to have a classical current and a superposition of both flowing and not flowing through a wire. It is still unclear if any of these are more beneficial than the others, and it is even more unclear if all future quantum computers will be built from the same technology or if there will be many different types of quantum computers available. That's all for today. See you in another video.